Professor Kuadel will be taking over on Wednesday, and his sessions are scheduled in Zoom. So on Wednesday, you'll start connecting in Zoom, and it's in the Canvas Zoom page. The links are in there. It's in with your lab scheduled stuff. Okay. So we won't be in Meets or in WebEx next time. Okay.
What would the format for the exam look like, or the module test look like?
The module test, the first module test is on February 4th. It's a Friday evening. It will be delivered to you in WebAssign, but then you'll write out all the answers and submit them in a PDF in Canvas so that they'll all be hand marked. It will likely be, I haven't made the test yet, but it will likely be, I'm guessing 3 questions. Similar to the question 7 that you write out and hand in. So there could be, you know, derivation, calculation. We want to see you explain things in writing. And you have an hour and a half for the test. So we will make the test so that you can do it in an hour and a half, in 90 minutes. Does that help? Is there anything more specific that you're wondering?
No, I just, that was good. That was good.
Okay. Okay. It'll be written as opposed to multiple choice, if that helps clarify. Anybody else? When you're writing these tests, like if there are 3 questions and the test is 90 minutes long, and you find after 45 minutes you're still on question 1, it's a really good exam writing strategy to keep track of the time as you go and put that question that's taking a bit too long away, work on another one that you may be able to get done quicker and gain yourself some time back. So time management during exams is something that you can practice, I guess. It's probably been a bit weird while you've been learning remotely and doing everything online, but this will be sort of like an in-person test, in that you get it, you write it all out, and then you hand in your written work. If we're back to in-person learning by the time of the second module test, that test will be in person. But this one will be remote. The first one will be remote. Okay, let us finish up the work on capacitors. And I know you've done a class on resistors in combination. So you've done probably Kirchhoff's voltage law, you know, adding up voltages around loops in a circuit and stuff. So we'll be doing similar stuff here with capacitors. And some people find this a little bit more problematic because you have to remember what the charge is doing. It's not just the voltage drop when you're solving some of these questions. You also need to think about the charge on the plates of the capacitor. So it's a little bit different from resistors that way, but you do have some familiarity with how to analyze circuit elements in series and in parallel. So we're going to do that for capacitors today. So when you combine capacitors in parallel, that means that when capacitors are in parallel, the ends of each capacitor are tied to the same high or low voltage on the battery. So you can see here, the top plates on these capacitors are all tied back to the positive terminal, the high voltage terminal on the battery, and all the negative charges here are on this is a negative Q3 and a plus Q3. The bottom side of the capacitors are all tied back to the negative plate. And in currents, or when currents are flowing around a circuit loop, it's only the electrons that are doing the moving, but it's sometimes helpful to imagine that the positive charges move too. So if we want like a helpful way to simplify thinking about this, we can think of positive charges coming out of the positive terminal and being deposited on the positive plates, right? And then the negative charges coming out of the negative terminal and being deposited on the negative plates. So the plates that are basically connected electrically to the negative terminal of the battery have negative charge on them, and the sides of the capacitors that are connected electrically to the positive terminal of the battery have positive charges on them. We know in reality that the positive charge plates are positive because the electrons have left them and been attracted towards the positive terminal of the battery, but we can imagine positive charges coming out of the positive terminal, negative charges coming out of the negative terminal, and they populate. They basically sit on the plates of the capacitors there, okay? So in parallel, each capacitor basically has the same voltage drop across it. So we have the same voltage drop, and then each capacitor has its own capacitance, and then each capacitor holds its own charge. Okay. The total charge that is out basically in the circuit that's away from the battery is the sum of all of the charges on the plates of the capacitors that are in parallel. Okay. So when we add them up, like Q1 is equal to C1 delta V. Q2 is equal to C2 delta V2. Q3 is equal to C3 delta V. And they all have the same delta V, and the parallel combination of the capacitors still has the same voltage across it, so we can use that to find our equivalent capacitance of capacitors in parallel. The delta V's cancel out, so we just get capacitors in parallel are a simple addition. So it's the opposite of resistors. So it's the same kind of math as the resistor cases, but for capacitors in parallel, you add them up. For resistors in parallel, you have to add the inverses, right, to get the equivalent parallel resistance. So for capacitors in parallel, you have to add up the capacitance, simple addition, okay? Everybody understand why that happened, why we were able to make those charges equivalent? Hopefully that's okay. Okay.
Sorry, could you explain the charges one more time?
Yeah. Each capacitor in parallel has some charge on the plates, right? And then each capacitor also has the same voltage across it because they're all electrically connected on each side, right? So each capacitor has the same delta V on it. There's a whole, like, all of the charge that's out in the circuit, it's equal to Q1 plus Q2 plus Q3. That's the magnitude of the charge on the plates of all the capacitors together. So this is how much charge is out in the circuit away from the battery. And if we had an equivalent parallel capacitor in there, we would expect that that whole amount of charge is still out in the circuit. So when we add these up, we would say Q parallel times the capacitance, the equivalent capacitance of the parallel combination, is equal to Q1 delta V plus Q2 delta V plus Q, oh, sorry, I mean to put C's in here. C1 delta V plus C2 delta V plus C3 delta V, because of the definition of capacitance in terms of charge and delta V. Oh, what am I doing? I need a C parallel here. Okay, so all the, oh, I have a C parallel. Oh my goodness, what day is it? Plus C3 delta V, this needs to be a delta V here. So Q parallel is C parallel times delta V, and then we add up all the contributions of the total charge, and you divide through the delta V's, and you get the parallel equivalent is C1 plus C2 plus C3. Okay, so you find it using the sum of all the charge that is out on the plates. Okay, and knowing that they all have the same voltage across them because they're basically tied to that, the battery terminals in each end. Okay, so capacitors in parallel are added, simply added capacitors in series, I bet you can guess where we're going. they're going to end up being added inversely, but I'll tell you why. So when we have a bunch of capacitors in series, the negative terminal of the battery pushes out some negative charge Q. Because it's a capacitor, it has to have the opposite charge on the other plate. Then because this is just a wire tying these two together, it has to be electrically neutral, and you end up with minus Q on the plate beside it. And then because you have minus Q on the plate, you got to get plus Q on the, the partner plate of the same capacitor. And then we've got a wire connecting those two that has to be electrically neutral. So we've got a minus Q on the neighboring negative plate of the capacitor. And then because of the definition of capacitance, we have to have plus Q on the other side. So we end up with minus Q plus Q, minus Q plus Q, minus Q plus Q. So the charge that's out in the circuit from the battery is basically just these two. The rest are induced onto the plates. Like between here and here, between C1 and C2, you split the charges that are already there, and you move them, minus Q close to the top plate and plus Q close to the bottom plate. But overall, the total charge here is 0. And the same is true for this. It's just that the top plate, the very top plate, that's charged at plus Q basically attracts minus Q to the neighboring, to its partner plate in the same capacitor. And then that repels minus Q to the next capacitor in the series. Does that make sense? So there's only this, and only this has come from the battery itself. The rest respond to that, and they separate out between the capacitors in series. Okay? And every capacitor, because it's in series and they are tied to the capacitor next to it, they each have their own voltage this time. Okay, so we have a voltage drop across C1, delta V1. We have a voltage drop across C2, and then we have a voltage drop across C3, delta V3. Okay, so when you do your Kirchhoff's voltage law, this total voltage drop is delta V1 plus delta V2 plus delta V3 of all of these elements in series. Okay, so as you go around the loop, here's your battery, here's capacitor 1, capacitor 2, capacitor 3, delta V1, delta V2, delta V3. So you do your Kirchhoff's voltage law, and you find the sum of the voltage drops, and they have to equal what's on the battery. Okay, this I think you've done. I hope I'm not gaslighting you like I did on the first day, which I still am very sorry for. Okay, so we do Kirchhoff's voltage law. We find all of the voltage drops in our loop, right? We go around here. And because of the definition of capacitance, we know that delta V1 is Q over C1, delta V2 is Q over C2, and delta V3 is Q over C3. And every capacitor has Q charge on it because of the way it has to balance out in those series connected elements. Okay. And then if we're trying to find our equivalent series circuit, we have to remember that the amount of charge that's out in the circuit from the battery is just Q. This Q here, I'm going to use air quotes, I don't know if you can see my picture, but that's all the battery can see out in the circuit. Okay, that's all that the battery is pushed out into the circuit. So as far as the battery is concerned, there's a charge of plus and minus Q on two plates at the end of this series of capacitors. So it only sees those two end plates. Okay, so that's why we can put a charge Q in with the equivalent series capacitance of the circuit. Okay, does that make sense? And then Q's cancel out, and you get the equivalent capacitors in series, the equivalent capacitance of capacitors in series is found using the inverse sum. Okay, and again, this is opposite to resistors. So if you found a way to remember how the resistors work, that's good because it means you know that capacitors do the opposite, so you can remember those too. But I'll give you a few memory tools to help you with that. Thank you. Okay, so capacitors in series, we use the inverse sum to find the equivalent capacitance of that series combination. Okay, and remember, the battery only sees this Q that goes out, that it provided to the circuit in a series capacitance situation. Okay, then, okay, so here's some things to help you remember this. The definition of capacitance for parallel plate capacitors, remember, is epsilon naught times the area of the plates divided by the distance between the plates. So you can hope maybe this will help you having a physical reason why the parallel combination of capacitors is simply an addition. Basically, what happens is if you put capacitors in combination in parallel, it effectively increases the area of your equivalent capacitor, right? We have the same voltage here across all the capacitors, okay? So we effectively have an area combination of all of them together. So when you increase the area, you increase the capacitance, right? And when you combine capacitors in parallel, the equivalent parallel capacitance is always larger because it's a simple sum. The sum of all of the individual components is always comes out as a bigger number than any of the individual ones that you put in. Okay, so if you imagine capacitors in parallel, you're effectively making one big capacitor with a large area A. So it gives you a bigger capacitance in total. Okay, that's how it's acting. They're obviously not like touching each other, being like bigger area like one device, but that's how you can think about it.
Sorry, what is D?
Sorry?
What is D?
D is the distance between the plates of a parallel plate capacitor.
Okay, thanks.
Yeah, and we'll use that on the next slide here. Thanks for the question. So for the capacitors in series, you effectively are increasing the distance between the plates. So if you put a bunch of capacitors in series, you basically have the same Q charge on all of them. You just are basically adding up the spaces in between to increase the distance between your plates, the effective distance between your plates. So when you look at the formula for capacitance, the distance between the plate is on the bottom. So if you make D bigger, the capacitance has to go down. Okay, so for the series capacitors, the equivalent series capacitance is always smaller than any individual capacitor that you combine to put together in series. Okay, so this is just if you like this mechanical kind of, you know, hands-on practical way of thinking about this, this might help you remember. You can also use, like, you know, phrases, mnemonics, memory tools. Capacitors in series add inversely, or CSI, like the show. Resistors inversely when parallel, RIP CSI. And any of the memory tools that you have for resistors also help here because capacitors are the opposite. They behave the opposite, oppositely to resistors. Okay, so resistors in series, you just add them. Resistors in parallel, you add inversely. Oh, what do I got here? Oh no, this is right. Yeah. Okay. Okay, so let's do a question. And this is where you'll see that the charge thing is something you're gonna have to get a handle on. It's kind of the new thing here. Okay. I think you'll be okay. I get the idea that you'll probably be, or have the idea that you'll probably be okay with combining series and parallel capacitors, because you can memorize the formulas. But when it asks you to find the charge on each capacitor in this scenario and the voltage drop, those are things that are a little bit more complicated, I think. And that's where the learning will have to happen here, I think. Okay, so we have a set of capacitors combined in series and parallel. They're hooked up to a 12-volt battery or 12-volt power supply. And we're asked to find the charge and the voltage across each capacitor. Okay, so the first thing we'll have to do is to find the equivalent capacitance, because we'll need to know that. We can do that. And then we'll use that to kind of work backwards to figure out the voltage drops and the charge on each capacitor. Okay, so we're given, here's our plus minus. It's hard to do voltage sources and capacitors, because if you're doing them quickly, they sometimes look the same, because you don't always have your lines the same for capacitors. Okay. So this is 12 volts. This is C2, this is C3. C1 is 9 microfarads, I think. Yeah. C2 is 2.5 microfarads. C3 is 1.0 microfarad. Okay. Let C4 be this. Okay. So let C4 be the equivalent capacitance for C2 and C3. They're parallel, right? So C4 is C2 plus C3. We have CSI, capacitors in series, add inversely. So that means capacitors in parallel, you just add them up. Okay, so we have 3.5 microfarads. Okay, so that's the first part. Now we've got C1 and C4 in series. So we'll figure out the equivalent there. I'm gonna go to the next page. If you're not ready, just let me know. I'm gonna make a new page. Okay. So here's our series combination. So capacitors in series add inversely, CSI. So 1 over the equivalent capacitance for the whole circuit is equal to 1 over C1 plus 1 over C4. So the equivalent capacitance for this circuit is 2.52 microfarads. Okay, great. I'm just going to write this out in a different way. So here's our voltage from our battery. It pushes out plus Q1 minus Q1. Okay. So this is capacitor C1 and this is capacitor C4. So capacitor C1 was always on its own in series with something else. So whatever the battery, like the charge that the battery pushed out to the circuit is Q1. That's the charge that's sitting on C1 because it was always by itself here. And then the minus C1 ends up being the charge on this parallel combination, or minus Q1, pardon me, ends up being the charge that's split onto these two plates. Okay, so we're going to have plus Q1 here and then minus Q1 somehow distributed on those two plates, which we'll figure out in a moment. But the battery just sees plus Q1 and minus Q1 going out, okay? Okay. Because this C1 was on its own, it's kind of defining this problem. We have delta V1 and we have delta V4, and V4 and C4 are related to that parallel combination, okay? Is everyone following this? It's this thing that's the key to this problem. Knowing that C1 was on its own, so whatever was on C1 is kind of cascading down to define the rest of the problem. Okay. So the total charge that the battery sees is Q1. Okay. I'll go to the next page when you're ready. So we've got I'm going to draw a diagram on the next page. So we've got our voltage source, we've got our equivalent capacitance, we've got Q plus Q equivalent minus Q equivalent. This is delta V, and this has to have delta V across it in order for the Kirchhoff's voltage law to work here. Okay, so this is for our equivalent combined capacitor circuit. So Q equivalent is equal to C equivalent times delta V, but Q equivalent is equal to Q1. Okay. So Q1 is equal to 2.52 times 10 to the minus 6 farads times 12 volts. So, oops, that's Q1. So Q1 is equal to 30.24 microcoulombs. Does everyone understand that? Anybody got any questions there? It's this thing equaling Q1, which is the challenge, I think, here. Okay. Then delta V1, using the definition of capacitance, is Q1 over C1. And that is 30.24 microcoulombs over 9.0 microfarads. I haven't put my 10 to the minus 6s here because those 10 to the minus 6 factors cancel out. And we get 0.36 volts equal to delta V1. So we've figured out the charge and the voltage drop across capacitor 1 after all that. Okay? Everybody okay? Sounds like it. I'm assuming so. I'm going to go to the next page.
How did you describe? You said that was the charge of. Could you just? Oh, sorry, I was writing down what you described that as. That is the charge of C1.
That is the charge. Yeah, charge on capacitor C1. Okay, so when you
Sorry about that.
No, go ahead. Sorry, I interrupted you.
Or I was just thanking you and saying sorry for interrupting. Thank you.
Oh, right. All the politeness. Okay, thanks. Okay, I'm going to go to the next page.
Excuse me.
Actually, yep, go ahead.
Hi. Can you explain to me why the total charge is equal to the Q1?
Yeah. If we go back to here, actually, I'll draw a new diagram. Okay. So we have delta V plus minus. We have C1, C2, C3. So C1 has Q1 plus Q1 and minus Q1 on it. C2 has plus Q2 and minus Q2 on it. And C3 has plus Q3 and minus Q3 on the plate. Okay. We don't know what they are, but we know the definition of a capacitor. If we have capacitance and voltage, then the Q is related to those things. So the battery, when it provides charge to the circuit, out of the positive terminal, it provides Q1. Okay. And then out the bottom of this, it provides minus Q2 and Q3 to the bottom plates in this combination. That's all the battery does. Anything that's in here on the plates that are not directly connected to the battery, all of those are induced charges responding to what's going on at the very edge that the battery is actually connected to. So the battery pushes out plus Q1 to the top side of this circuit. And well, we have to think about it that way. Well, let's think about it that way. And that means that it also should push out minus Q1 to the other side of the circuit. Okay. There's no more charge being pushed out the positive terminal than this plus Q1. So basically, the circuit or the battery, when it's connected out into the circuit, all it knows is there's plus Q1 on the positive side and minus Q1 on the negative side. Does that make sense?
Yes, that makes sense.
Yeah, and anything in between those edge plates is all charge that was already there, but it's just being separated and moved around inside. Okay, so these two charges here are due to the battery directly. Okay, and then all of these other ones are induced or moved charges. Okay, so when the battery, like imagine you're the battery and you are connected to the ends of these two these two capacitor plates, one on the high voltage side and one on the low voltage side. You don't know what the capacitors look like, how many there are and how they're combined. All you see is an equivalent capacitance and then the charge that you provide to that equivalent capacitance. So that's why we have this. The battery just sees a capacitance out there with a voltage drop across it that's equal to the voltage drop across the battery. And then because of the way the battery has to push that charge out there, we know that the equivalent capacitance in this case has to be equal to Q1. Okay.
Okay, thank you.
Yeah, you're welcome. This is the sort of new part of the combination in parallel and in series. You don't really have to think about this in resistors because the charge actually travels through the resistor just more slowly. In our case, the charge gets moved out of the battery and then gets stuck there on the capacitor plates. So we have to actually think about how much charge builds up out there. Okay. So I'm gonna make a new page here. Let's go back to C1 and C4. This is our parallel combination here. So we have delta V, delta V1, delta V4. We have plus Q1 minus Q1 plus Q1. Okay, so the battery sees that. Okay. If we do Kirchhoff's voltage law and we go around this circle, we know that the voltage gain through the battery is equal to delta V1 and delta V4. I'm not sure how you used to add these, but hopefully that makes sense. Or you can write 12 volts minus delta V1 minus delta V4 equals 0. You can do that either way. Okay, so delta V4 is equal to 12 volts minus 3.36 volts, which is what we just calculated for V1. Delta V4 is equal to 8.64 volts. Okay. Are you okay with that? Hopefully that is more familiar with something you already know. Now, V4 is actually a combination of, or C4 is C2 and C3. Okay. And they are tied. They are tied here. C2 and C3 are the parallel capacitors that are the equivalent of V4. Okay, so the two parallel capacitors C2 and C3, they both experience a voltage drop of V4 because they are tied here. Okay, so there's a delta V4, oops, I can draw that like a normal person, delta V4 across those based on how we've defined V4. Okay. Delta V4. So that means we know that delta V4 is equal to delta V2, which is also equal to delta V3. Does everyone get that? All those capacitors are tied, like have the same voltage on each side. So the voltage drop across C2 and C3 are the same. And they're the same as they have the same voltage drop as the equivalent parallel combination. Okay, and we've just calculated V4. So it's 8.64 volts. Okay. We just did that here. Everybody okay with that? Okay, we'll make a new page. So we've got all the delta V's now, and we know all the C's, so we can find the remaining Q's. So based on the definition of the capacitance, Q2 is equal to C2 times delta V2. So it's equal to 2.5 microfarads, 8.64 volts. Okay, so Q2 is equal to 21.6 microfarads. And Q3 is equal to C3 times delta V3, and that's 1 microfarad times 8.64 volts. So Q3 is equal to 8.64 microcoulombs. Okay.
Hey, sorry, is the first one units correct? Is it microcoulombs as
Oh,
well?
microcoulombs, thank you.
Okay.
Thank you. If you add these up, Q2 plus Q3, that's equal to 30.24 microcoulombs. Let's just zoom back up here and see what we've got for Q1. Q1 is 30.24 microcoulombs. And that's what we expect, because remember we had Q1 plus Q1 minus Q1, and then we had Q2 and Q3 had to have the equivalent of plus Q1 in their combination, and then minus Q1 in order for this to have plus Q1 minus Q1 plus Q1 minus Q1 in series. So the fact that Q2 and Q3 have the same total charge as Q1 is a good check. Okay.
Wait, sorry. So finding V1, we had to do Q over C, but then for Q2 and Q3, or sorry, I guess V2 and V3, it doesn't matter what their C is. They're automatically equal to each other. Does that make
The voltages are equal to each other.
okay?
Yeah, because, whoops. Let's go back here.
But,
Because
like,
when you do your Kirchhoff's voltage law, there's a voltage drop across C1, and then there's a voltage drop across this combined pair of capacitors, and C2 is at this voltage here. Let's call this VA, and this is VB. C1 has a voltage drop of VB minus VA across it, or VA minus VB, whichever way you want to calculate that. And C3 also has the same voltage drop across it because they are connected together by wires at the ends. Okay. There's no other voltage source in there, so the voltage drop across each has to be the same.
So it does split equally. Even it does split equally, even though C3 and C2 have different, whatever that unit is, micro F.
Yeah.
Capacitance.
Yeah. Yeah. They have the same voltage drop across them because they are basically tied together at the ends. So when you do Kirchhoff's voltage law, you have, 12 volts here, 12 volts, 12 volts, and then you drop some voltage. So then you have like, I don't know, I can't remember what our actual number was, but let's say we end up with 10 volts here. So you have 10 volts here, and this wire here is attached to each end of the capacitor. And if you came out the negative end of the battery, you'd be at 0, 0, 0 volts. So if you were at like 10 volts here and 0 volts here, each capacitor sees a 10 volt drop at each end where it's connected into the circuit.
Sorry, your mouse has frozen again, so we just need you to draw stuff when you're pointing it.
Yeah.
Thanks.
Okay.
Thank you.
Yeah. So if we're going around this, thank you for the reminder. If we're going around here, we drop some voltage there. Let's say we get down to 10 volts, okay? We get 10 volts by the time we get here. On the negative terminal of the battery, we call that 0 volts. So we come around here and we're at 0 volts. So C2 sees on one side of it 10 volts, on the other side of it 0 volts. So it has a drop of 10 volts across it. C3 is tied into the same circuit, so it sees 10 volts on the plus side and 0 volts on the minus side. So they both have 10 volts across them. And then the amount of charge going to each is going to change. And that's how the circuit responds to the capacitance. So both capacitors have 10 volts across them because they're tied together electrically on the ends. And then some charge will flow to C3 and some charge will flow to C2 to make up the capacitance that gives you 10 volts across them. So it's the Q that adjusts in that case.
Okay, yeah, that makes sense.
Okay, good.
Thank you.
Thank you for the reminder about my mouse too. Okay. So I see a hand up. Yep, Dimitri.
Just a quick question. Is the assignment that is like released this week, is it going to be on this material or is it going to be on the material taught by the next section of the class?
Assignment 3 has 2 questions from my material up to today, and then 5 questions from Professor Kudel.
Okay, thank you.
Assignment 2 is all electricity stuff. So I think there's combinations of capacitors. Oh no, it's potential mostly. Mostly potential in the definition of capacitance. Well, there's probably this on the next assignment. I can't remember specifically. Okay. Okay. So the challenge is to that charge going out into the circuit. That's the thing that is the different thing you need to think about here compared to what you know about resistors. Because you've done resistors in series and parallel, but because they're all loops where the charge keeps moving. You don't have to imagine charge building up anywhere when you're dealing with resistors, but with capacitors you do. Okay, so that's the new thing here to really focus on and try and get a handle on. Okay. Okay. So energy stored in capacitors. We have a potential difference across capacitors, and we have a charge separation. So that means if we've got a voltage or if we've got a potential difference, that means we must have a potential energy difference, and that's the energy that we're talking about. We've used a battery or a hand crank or whatever to put charge on a capacitor, and it's been pushed there, and now we're just holding it there. So it's got some potential energy, which the delta V of that capacitor tells you. Remember, delta V is equal to delta U, which is equal to minus the work, which is equal to minus delta K, which is the kinetic energy. So work, kinetic energy, potential energy, and potential are all connected together. So as long as we have a delta V on a capacitor, we have stored energy. Okay, so when you close the circuit here and you start building up charge on either side of the plates of a capacitor, you're doing work to move the charges there, and then they get stuck on the capacitors, and you have basically potential energy stored there. Okay, see a hand up? Yep.
Is there like a limit to how long a capacitor can store a charge?
There's always going to be kind of leaky, leaky sort of loss of energy. If you have a problem with your computer, have you ever been told to shut it down and to leave it for a minute or two? What you're doing is
Reset in
giving
the CMOS battery?
Pardon?
Like reset in the CMOS battery type thing?
Maybe, but not a battery, but if you shut your computer down and turn it on right away, it's possible that capacitors will still have charge left on them if you don't let them completely discharge. And those can, be setting switches like, high voltage, low voltage, it can be. So when you restart a device that you're having trouble with, you let it sit for, 1, 2, 3 minutes. And that lets all the charge on any capacitor just dissipate into the circuit. And then when you turn it on, everything is fresh and there's nothing set at high voltage or whatever. So you can lose charge because everything is connected electronically and nothing's a perfect energy store.
So
Okay, thank
what
you.
is what is the point of a capacitor? Like, what do we use them for?
You use them to store charge for when you need it fast. And it also, you'll learn in the second part of in the second module, it's also used in combination with other devices to do other things. But for our purposes, we're putting the charge on the capacitor to hold it. One example, in old clacky keyboards, each key used to have a capacitor associated with it. And you would literally, like, when you pressed the key, it would move the plates together kind of and short out the capacitor, and then you get a signal saying, oh, someone's pressed that key. So you get a little current flowing when you actually shorted out that capacitor. So they're often used to provide energy quickly. We're going to do an example later. Defibrillators are a really common example. They store a lot of energy, like they build up their energy, and then when you try to restart someone's heart, they get a blast of energy really quickly.
Okay, thank you.
Yeah, you're welcome. So when anything has a potential energy, it means that it has the potential to do work or to be used in some way. So the keyboard, the defibrillator, those are very straightforward usages for a blast of charge all at once. When you get to module 2, you're going to start looking at how these things, you build up charge and let charge go over time, and you can control like the increase and decrease in the rate. So you can do different things then when you've got capacitors in combination with resistors and inductors and other elements. But for us, we're just considering what you could do with just charge. and what happens if you just let it all go at once. That's kind of what we're doing right now. Okay. So, if any of you have ever used an old-fashioned camera, I was just looking at my late dad's old camera on the weekend, and it has a flash on it, and you got to charge it up, and you can hear it kind of go. You can hear this high-pitched noise going up, and then when it flashes, like it just lets all of the charge go in the flash bulb, and then you got to wait for it to charge back up again. Yeah. Okay. So I'm just going to basically give you the definition here. The energy stored in a capacitor is due to the separation of charges, which produces an electric field. This is kind of a weird title, but basically a capacitor has charge plus and minus separated, and that separation of charge, we already know if you have plus charge plate and a minus charge plate, you have an electric field there. So we've put some plus Q and we put some minus Q, and it's just sitting there waiting to be used somehow. Okay, so this is just the definition of the potential energy of a capacitor once it's charged up with charge Q and has a delta V across it. Okay, so there's different ways to combine this given the definition, the equation defining capacitance, but pretty much this is how it goes. If you actually wanted to put the parameters in for a parallel plate capacitor, you know that the voltage difference or the potential difference across a parallel plate capacitor is equal to that, uniform electric field magnitude times the distance between the plates. And the definition of capacitance for a parallel plate capacitor is this, and then you get this version in terms of the electric field and properties of the capacitor. Okay, so it's like, imagine, our gravitational example. If you lift an object through a gravitational field is still existing, but the object isn't doing anything, but it has potential energy that can be released if we drop it. And the same is true here. We have an available source of energy that if we need it, we can use it. Okay, so let's do the defibrillator example. It's very brief. This example is very brief. Given 400 joules of energy over 10,000 volts or 10 kilovolts, what's the capacitance of this defibrillator? So it's basically plugging numbers into the equation, okay? So given total energy, U is 4.0 times 10 to the 2 joules, and we're told delta V is 10 kilovolts or 10 to the 4 volts. And we want to find the capacitance, so we can find that through U equals 1/2 CV squared. So C is equal to 2 times U over delta V squared, or V squared. This is I should say this is an implied delta V in the formula. So 4.0 times 10 to the 2 joules over 1 times 10 to the 4 volts squared, and C is equal to 8.0 times 10 to the minus 6 farads equals 8 microfarads. Okay, so that's straight up substitution into the formula. Okay. So once you use the defibrillator, you've discharged all the charge into someone's heart, into their body. You would have to wait for the battery to build up the capacitance or build up the charge in the device again. So it takes a little longer to charge it up, but once it's charged up, you can use it really quickly. Okay. Right? Good. So this is, these formulas are on the formula sheet. You can find them. Oh, I have delta V's here. I should keep my delta V's here then. This was a delta V all squared. I see your hand up, yep.
So with somebody that's practicing, like a surgeon or somebody, would they have to use these formulas to calculate the amount of energy, like, to put into somebody if they had to?
I don't know, because I've never been in a, you know, in a emergency room or whatever when they're being used. You see in TV shows where they say charge to whatever. So I don't know if they actually have to do that. Maybe someone on here has an idea, has some experience. Presumably, like a defibrillator in a, you know, hockey rink or something is probably pretty standard. So it has, you know, a charge that it charges to. But I don't know about more advanced devices in, you know, an operating room or something. But the ones for the general public have to be pretty not difficult to use. Like you shouldn't need to know how much to charge it up to use it. You just use it. So capacitors, we can enhance their ability to store charge. We have discussed capacitors with plate, like we've discussed parallel plate capacitors. We did spherical capacitors last time. We did just a sphere, like relative to infinity. And all of those examples, we just had air or a vacuum around them. We weren't thinking about what was put in between them. So this epsilon naught factor is a constant, and you use it when the capacitor is filled with air or a vacuum. But if you put something in between the plates, if you put what's called a dielectric material between the plates of a capacitor, it will increase the capacitance by a factor of kappa. Okay. So it means the capacitor can basically store more charge for a given voltage. Okay. And it's because of the way this material works, and hopefully we get there by the end of today. Oh, I hope we can. So we have if we put what's called a dielectric material between the two plates here, for example, it effectively provides a little bit of electric shielding and allows more charge to come up to the plates in some cases. Okay. So what we used before was epsilon naught. And if we put a capacitor, or if we put a dielectric in the capacitor, it increases the capacitance by this factor kappa. So in all the formulas where we have epsilon naught, if you have a dielectric in your device, or if you add one in, then you have to change from epsilon naught to epsilon. And they're related by this scaling factor K. And here's an example. Air is not exactly 1, but it's very close to 1, which is epsilon naught, which is the permittivity of free space or vacuum. Other materials have higher values, so glass, Pyrex glass is 5.6. Paper 3.7.
Were we just considering it to be air in between the plates before?
Before it was we didn't say it was air or vacuum, and we use those interchangeably because this is very close to 1. Epsilon naught is for a vacuum, but we use it for air also. Okay. Okay. So I'm not going to say much more here, except that if you put a dielectric material inside a capacitor, it increases the capacitance of the capacitor. Okay, so let's talk about how this works, and then we'll hopefully have time to talk about why it works. So we've got two cases. We can have a capacitor device that's either connected to a battery and charged up, or one that's been charged up and then you disconnect from the battery and it's still holding that charge. So that's called an isolated capacitor. We have two kinds, isolated and powered. So an isolated capacitor, we charge it up and then we disconnect the battery and we imagine that the charge just stays there on the plates. We have no way of losing it. Okay, so you charge up the capacitor, And then you disconnect the power source. The charge on the plate stays the same because there's no battery hooked up to be able to provide more charge if you need it. So Q stays the same. Q sub 0 is the amount of charge that we have, like when we've charged it up and it's hooked up to the battery. Then we remove the battery and we put in the dielectric material and we consider the charge after. But because the battery is disconnected, there's nowhere you can draw extra charge from, so the charge stays the same on the plates. So if you put a dielectric material, so we have the charge on the plates and the voltage and the voltage across the plates. So we have the definition of the voltage across the capacitor with the dielectric. So this is with dielectric. Okay. So Q is the charge with the dielectric, C is the capacitance with the dielectric, and delta V is the new voltage after you put the dielectric in. So all of these terms with no sub-zero are all the conditions after you put the dielectric material in. We know that the charge stays the same, so you can write it as Q equals Q naught. And we know the definition of capacitance when you put the capacitor in. So this is the original, C naught is the original capacitance, and C is the capacitance after you put the dielectric with constant, with this dielectric constant kappa in. So we replace C with kappa C naught. Q naught over C naught is the original voltage across the capacitor when you first charge it up, and you divide it by K. So when you have a capacitor that's holding charge but isn't hooked up to a battery, and you slide a dielectric in it, the voltage drops. Okay, by a factor of kappa. Okay. Now, when we put the capacitor, or when we put the dielectric in, we get a higher capacitance. And remember that Q and C and V all have to compensate to hold everything the same, basically. So when Q is the same and the capacitance goes up, the voltage has to go down. Does everybody understand that? We charge up a battery, we take the battery, or we charge up a capacitor, we take the battery off, we put a dielectric in the capacitor, and what we see is a voltage drop across the capacitor after we put the dielectric in there. Okay, that's just a fact. I'm going to tell you about a powered capacitor, so maybe that'll help. That makes sense of the previous one, because together they form a more complete picture. So we'll charge a capacitor up and we'll leave it connected to the voltage source. That's a powered capacitor. Okay, so that holds the voltage across the plates the same because they're still hooked up to the plus and minus, the high and low side of the battery. They see the same voltage no matter what we do. The battery controls that. If we put a dielectric between the plates of a powered capacitor, it basically means we increase the capacitance. That means we can draw more charge up from the battery and hold more charge there. Okay, you charge up a capacitor, leave it hooked up to the battery, so it still has a delta V across it. And it's also hooked up to a battery which can supply more charge if we want it to, if it needs to. You put a dielectric in, which increases the capacitance of the device, which means we need to draw more charge up to the plates to keep delta V, C, and Q all in balance. And when you write it out, these are the values after you put the dielectric in. We know the definition of capacitance before and after the dielectric, so we put that in. The voltage is held constant, so you can replace delta V with delta V naught, and you come out with this here. So if you have a capacitor hooked up to a battery and you put a dielectric in it, it will draw more charges to the plates from the battery, okay? In the unpowered case, if you charge up a capacitor and disconnect the battery, you have no source of extra charge. So all the dielectric will make this do, the capacitor do, is reduce the voltage, okay? So an isolated capacitor, when you put a dielectric in it, a charged isolated capacitor, when you put a dielectric in it, the voltage will drop. But a powered capacitor, when you put a dielectric in it, the charge storage will go up because the battery is still connected and can supply some charge. Does that make sense? This isn't really mentioned very much in the book, but there's an example on it that kind of assumes you can figure this out, but it's kind of subtle, I think. Okay, an application of this, like putting a dielectric in a capacitor, is actually a stud finder. So when you're running a stud finder device over drywall, if there's just air behind it, that has, you know, epsilon naught, and it has kappa equals 1 roughly. And once you come across a piece of wood, it has a different capacitance. So it changes the capacitance, and the device can measure this as a change in voltage or a change in charge. I'm not sure actually how it does it, but that change in capacitance when you run the device over a material with different kappa. I don't know if wood is in here even. I don't see it, but you know, wood has a kappa value of about 2. Okay. All right. Somebody asked about this last day. If you hung around a bit after the lecture officially finished, you can put a high enough voltage on a capacitor to break down the air or the dielectric material between the plates or inside the capacitor. There's a maximum electric field that every material has before it, before it disintegrates, before the electrons are blown away from the nucleus of the material. So for air, it's 30 kilovolts per centimeter, or 3 megavolts per meter. I showed this video last time after class. Oh, I'll show you Jacob's ladder here. This is a demo that we actually have in the department too. So it's got 2 wires that are hooked up to a high voltage supply. Oh, I seem to be giving you guys a Grammarly ad every day. Apologies for that. Okay. All right. So they put a high voltage supply across these wires, and where the voltage gets high enough, or the electric field gets high enough, where the electric field gets high enough, it breaks down the air and basically creates a little lightning bolt. See? And it creates the lightning bolt where the lines are closer together, because that's where the electric field is the strongest. Remember, electric field is volts per meter. So where the per meter is the smallest, that's where you get the strongest electric field. And then it's rising. Does anyone here remember why it was rising? We talked about this a little bit last day at the end. Why do you think that would be rising?
I think he said it heats up the air and then hot air wants to rise.
Yeah. The breakdown of the air releases a lot of energy and heats up the air around it, even where it's not broken down, and the hot air rises. So the little lightning, the little lightning bit is created where those two filaments are closest together at the bottom, and then the air heats up and it draws it up to the higher part of the. Let's watch this one. This was a better one. This was a power station. We'll see Grammarly again probably. Before. I don't know why. This is on 2. Okay, watch this. This is pretty good. That's the breakdown of air. So the electric field had to be higher than 3 megavolts per meter. Oops, I didn't mean to repeat that, but we'll watch it again. Okay. So you can put, like, you can basically accumulate charge on a capacitor until the point that the electric field that charge creates breaks down the material. And if you put, like, plexiglass is a dielectric material, if you exceed its breakdown, if you exceed its breakdown electric field, it will damage the material even. So this looks like, you know, kind of a feathery lightning stroke pattern. That's from the electric breakdown in the plexiglass. Okay. The table that I showed you before, I cropped off the third column here. So the dielectric strength, that's the electric field that causes the material to break down in time, and it's in units of 10 to the 6 volts per meter. So we'd already seen air is 3 times 10 to the 6 volts per meter. Okay.
So what's a common material that's used for capacitors?
Yeah, good question. I think like early on, like I think Bakelite was used in, you know, like World War II kind of capacitors because it was a common kind of insulating dielectric material. But these days, I actually don't know what they're made of now because they're so small. So that, you know, the distances have to be really, like, this two sides of the capacitor to be really close together. So I'm not sure what material they put in between, but I mean, you could probably Google it and find out. It's a good question. Good question. But the old, like, if you look back at, you know, World War II electronic devices, they've got these massive, like, you know, the size of your fist kind of things with, you know, you can see lines of like mylar or rubber or Bakelite in them to build up to the capacitance that they need, and also to adjust the spacing between those plates. It's kind of cool. Okay. So we had the energy equations for the capacitor with a the capacitor just straight up, and now we have the relationship between the energy stored in a capacitor with no dielectric and the energy stored inside the capacitor with the dielectric. This is an isolated capacitor. So again, isolated capacitor is disconnected from the voltage source and there's no opportunity to bring extra charge to the plates. So when you insert a dielectric, the energy goes down. So the voltage goes down and the potential energy goes down. Those are consistent. Okay. A powered capacitor has the voltage source connected to it, and as soon as you put the dielectric in there, the capacitor can draw more charge to it to basically increase the amount of energy it can hold. Okay, so this powered versus isolated capacitor, the difference that you have to think about is whether the capacitor can get more charge from somewhere else to either increase the energy or decrease the energy, or increase the voltage, decrease the voltage. Okay. I'm gonna do just a bit of background here, and then we'll come back to that question if we have time, and I'll explain why this dielectric material works the way it does. Okay. So a dipole is an atom or molecule that has like in its shape, like one side of it is noticeably negative and one side is noticeably positive. Water is an example of that because it has a triangular shape, like the two hydrogens attached to the oxygen in this kind of formula or formulation. So the water molecule is naturally a dipole. Okay, so dipoles, they have two polarities. That's what that means, dipolarity. You can induce a dipole. So let's imagine we have a nucleus and then a cloud of electrons around it. If you apply an external electric field to it, the electrons will basically shift in the direction opposite of the electric field. And that's the case here. So if the electric field is up, then the electron cloud will shift down. If the electric field is down, the electron cloud will shift up. So then we end up with something that looks like this. Okay? So if I put a negative charge here, it bring a rod close to a dielectric material, it basically lines up the molecules in the material so the negatives are repelled by the nearby negative charge. Okay, they respond to the electric field of this nearby charge. Same thing if I bring a positively charged object nearby, the minus, like the electron clouds will basically adjust themselves to line up closer to that. It'll be attracted to that. So it causes an alignment of molecules in the material. Okay, so here's an totally not aligned material. If it's a dielectric material and I chuck it into a capacitor, the electric field goes from positive to negative, and so it will basically cause the electrons to line up with the left-hand side, like the electrons will be oriented to the left and the nuclei will be sort of left on the right-hand side. Inside the material, the adjacent pluses and minuses all cancel out, but you're left with a net charge separation on the edge of the material, right? All these pluses and minuses inside cancel out, but you end up with a net negative and a net positive near your plates of your capacitor. Okay, so this is the original electric field that you applied, and now you have a little like mini capacitor that you kind of made by aligning the molecules in the material. So you end up with a little induced electric field inside. Okay, and so long as you don't bring any charges here, this main electric field from the main capacitor and this little induced electric field, that's what's responsible for the voltage drop when you put a dielectric inside an isolated capacitor. Okay, this gives you a little voltage change in the opposite direction. Does that make sense? Okay. Okay. If I had a powered capacitor, and put a dielectric in it, the battery or the battery would know that the voltage actually dropped a little bit when I put the dielectric in, so it would send more charge up, which creates a bigger induced electric field. So it basically goes back and forth until the charge all balances out and the voltage drop, the net voltage drop across the batteries or across the device is the same as across the battery, which is why the capacitance goes up, the charge is higher than it would be without the dielectric there. Okay. So this is basically describing what I said, and you can read this. So the capacitor plate itself has an electric field from the positive plate to the negative plate. And because of the induced alignment of charges in the dielectric material, you got a little electric field induced here, and that's related to a little voltage drop that goes against your main voltage drop across the device itself. Okay. Yeah, so here's the summary. An isolated device that you insert a dielectric into will see a voltage drop and a potential energy drop. A powered capacitor that you insert a dielectric into will see an increase in charge accumulation on the plates and an increase in potential energy stored in the device because you're bringing more charge up there and holding it. Okay. Any questions about that? Take a look through this. It's in the textbook too. Read that. You can read that section. And we'll try to do this quickly, this example. This is not a long one, so we should be able to do it in a couple minutes. Okay. So we've got a parallel plate capacitor that's empty. It just has air in it. It has some capacitance, 10 picofarads, and it's charged to a potential difference of 30 volts. The charging battery is then disconnected and ding, 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 that's an isolated capacitor now. And a sheet of mica, which is a dielectric material, is inserted inside the isolated capacitor. And we're asked to calculate the initial charge on the plates, the new capacitance once you put the dielectric material in, the mica, and the new potential difference between the plates. Because it's isolated, when we put a dielectric in, the voltage drops. So we should get a potential difference that's lower. And then we are asked to calculate the energy difference, or the energy with and without the dielectric material. Okay. So if we disconnect the battery, we'll have an isolated capacitor. Q is the same whether it's before or after you put the dielectric in, because it's isolated. The charge on the plate stays the same, and it's equal to C times delta V. Oops, C naught. Delta V naught. Okay, so we have 10 picofarads times 30 volts, which is equal to 3 times 10 to the minus 10 coulombs. I hope you can read that. Okay. The capacitance is kappa times the original capacitance. We have 6. The dielectric constant of mica is 6, and it's just a number. It doesn't have units. It's just a scaling number. And we have 10 picofarads. So the new capacitance is 60 picofarads. Okay. Delta V is Q over C. The charge remains the same. We have 300 picocoulombs, and we found the new capacitance, which is 60 picofarads. Again, I'm not going to write out my 10 to the minus 9s here, because our picos cancel out. 5.0 volts. Okay, so we went from 30 volts to 5 volts by putting that mica in, the isolated capacitor. Okay, I need a little bit more room than I have here, so I'm going to make a new page. We were asked for the original potential, or the original stored energy, 1/2 C0 delta V0 squared is 1/2 10 picofarads times 30 volts squared is equal to 4.5 times 10 to the minus 9 joules. And then U, which is the with the dielectric, equals 1/2 C times delta V squared. Those are the new values after the dielectric goes in. So we have 1/2 times 60 pico, or times 10 minus 12 coulombs. Is that pico? Oh yeah, nano is minus 9. Pico is minus 12. And then 5 volts, which was what we just calculated for the new voltage. So U is equal to 7.5 times 10 to the minus 10 joules. So you can see here, after the dielectric is inserted, the voltage and the energy go down. And that makes sense if it's isolated. Okay. Oh, trying to squeak that in. Okay. Anybody got any questions about that? Oh, glad we made it to the end, because that microscopic part is how you understand this. Dimitri, yep.
Just a question about the exam, really. Are you gonna post any practice material, or would it just be a good idea to review the assignment questions?
Yeah, review your assignment questions. Take a look at the practice concept questions in WebAssign, because those are good practice to help you make sure that you understand kind of like the so-called basics, like the underlying principles. And the questions from the assignments are quite similar, if not the same, to questions in the textbook. So for the end of each chapter, and we've done chapters 22 to 24 or 25 now, at the end of each chapter, there's a bunch of questions, and in the back of the book, there are answers to the odd numbered questions. So you can try, like, pick one of them and try a question and see what you get for the answer. Does that help?
Yeah,
But
thank you.
the exam questions will be quite like your homework questions and doable within the time allowed. So when the instructors make the tests up, we do them too, and we have to be able to do them in a lot less time than we give you to do them. So we do a check that way. Okay. And practice doing questions with the formula sheet, because it's closed book. You're on your honor, but it's closed book, and you'll have the formula sheet. And the formula sheet was just updated over the weekend. I went through and reconciled a few things related to kappa and epsilon and stuff, so that it's more consistent with what we're doing in class here. So there's new formula sheet as of yesterday, I think. Okay.
Could you go back a slide? I didn't get a screenshot.
Yep.
Thank you.
You're welcome. Sorry that was so fast. I wanted to get it done. But I'm glad we got to the end of the microscopic picture. Hopefully that made some sense. Okay. Anything else? There's a
So
help
now
session tomorrow night for assignment 2. Yep, sorry, go ahead.
so have we now covered everything that'll be on the test?
Today we finished module 1. So everything we've done to the end of
Okay.
today is module 1.
Okay.
Yeah. And while there won't be multiple choice questions, you might be asked, for example, to explain, why the voltage decreases when you insert a dielectric into an isolated capacitor. So understanding the concept is still important, but you won't be asked to do it like in a multiple choice format or that kind of thing. It would be part of a written out question where you justify your answer or whatever. So we've done all. I don't think there's any questions on the homework, for example, about the microscopic picture of dielectrics inside a capacitor. But having an understanding of that hopefully will help you understand how to do the mathematical questions. But you might also be asked to give like a one line, sentence explaining why something you got works the way it does. Okay. Okay. Anybody else?
Hello, I
Is
have
there
a
any-
question.
Yep.
On the formula sheet, you have equation E equals sigma over epsilon naught. Yes? And then right beside it, you have another equation that says E equals sigma over 2 epsilon naught.
Yeah, I know. E equals epsilon naught is the electric field for a single charged plate, like infinitely charged plane or plate. And E over 2 epsilon naught is for the capacitor when you put two infinitely charged, oppositely charged plates next to each other. So each E over epsilon naught, E over 2 epsilon naught is for one charged plate. And E over epsilon naught is the combination of two charged plates together. So that's the E over epsilon naught is the electric field inside a parallel plate capacitor because it's made of two charged plates.
Okay, thank you.
Yeah, it's yeah, that question comes up a lot actually, because it seems wrong, but it's the formulas for two separate configurations.
Am I allowed to write notes like that on my formula sheet before the test, or is that the kind of thing that
No,
shouldn't do?
no, we
Okay.
want you to do just the formula sheet as it is. Yeah.
Okay, great. Thank you.
Yeah. Yeah. Because, you know, who knows what people would write on there. So. You know how to solve the electric field due to a one single infinitely large charge plate using Gauss's law. We did that in class, and you get 1/2 epsilon naught. You can go back and look. Yeah, Dimitri?
So for the test, there's not going to be, well, is there going to be a Zoom meeting just for questions? And other than that, it's just, we just do it by ourselves?
For the test, like it's not proctored, if that's what you're asking. So for the test, there is a thing that we ask you to do first, which is a statement of integrity, where you, you know, click, I agree to, you know, abide by the rules of the test, blah, 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 close book, everything. And then you submit that to Canvas within a day or two before the test. So you have upon your honor said you will like abide by the rules of the test. So that's the first thing. And then once you do that, it opens up the WebAssign link for you to get the questions on the test. So you have to do that honor statement or the integrity statement first. And then once the WebAssign link is open for you, once the test period starts, you can go to WebAssign and get the questions. And then I recommend that you save them to your computer, like print them out to PDF or something in case your connection to WebAssign goes down. But those are the 3 or however many questions you will get for your test. And then you write them out. You have 90 minutes to do that. And then we give you a little extra time at the end to scan or take a snapshot of your written pages and convert them to PDF and upload them to Canvas. Does that make sense? So
Yeah,
the questions, the questions come to you in WebAssign, and you submit the written solutions in PDF format in Canvas.
So we can go on WebAssign at the beginning and get the questions, and then once we have the questions, we can close WebAssign and just work.
Yeah, yeah. There'll be nothing submitted in WebAssign.
Okay,
so some people might want to keep it open, you know, whatever. You can do that, but I would recommend, you know, exporting them in some format to your computer in case the WebAssign crashes or something. We had that happen during our midterm last year in 155, and it caused a major problem when everyone was trying to submit their answers. We were submitting answers in WebAssign then, and it was a problem. So I recommend when you go in, like capture the screen or whatever, so that you have the questions on your computer or print it out or whatever. Okay.
Sorry, is there a solution style? Oh, sorry.
No, go ahead.
Is there a solution style guide, like for the given, find, type features and whatnot?
No, we don't have a requirement for the given, find, assumption, solution format, but we appreciate when the questions are laid out that way because it helps us understand what you know and what you're trying to find. We like to see, well, when I write out solutions for you, I try to include enough explanatory information so you can follow my thinking as I work through the problem. We don't necessarily need quite as much description as I provide to you because I'm sort of still in teaching mode when I'm providing assignment solutions to you. But if you had a question where you're asked to find the electric field of a sphere, a uniformly charged sphere or something, if you need to use Gauss's law, when you write the equation, it helps if you say Gauss's law next to it. And it helps if you say, you know, the electric field and the surface area normal direction are parallel. So E dot dA is equal to E times A, or, you know, whatever. So if you can give us some idea of your thinking within reason, then even if you get the question wrong, we can understand what you're doing. Does that make sense? Like we could give you marks for method if we can understand how it works from step to step. That's not very helpful because it's not very precise, but you know, sort of the more information you tell us, and if you write it in a logical, like, you know, the next line is the next step, the next line is the next step, that helps us out a lot.
So if I were to, sorry.
No, go on.
if I were to do a question like this, if I wrote at the top that like it was an isolated capacitor and then use the equations for isolated, if I, for example, like identified it incorrectly and it was a powered one, then you could follow. Is that kind of?
Yeah. So if you said like this is a, the battery is disconnected, so it's a powered capacitor. Let's say you said that, and then you did all the steps for a powered capacitor. I could at least see like that one mistake led to the other problem, so I could give you some marks for the work that you did, because what you did, we try not to do a double jeopardy kind of thing, like you get wrong marks, like marks taken off for something that have marks taken off before. So we can see that you at least are in the capacitor dielectric space in your mind when you're doing this question, but you did a lot of work. It wasn't the right scenario, but at least we know that you're kind of part of the way there, if that makes sense. So we can try to find some marks in the work, even though you identify the situation incorrectly to start with, if that makes sense.
Okay, great.
So
Thank you.
We don't want you to write like a giant essay about every question, but give us some clue about what you're thinking.
Okay, so that means the marking style isn't binary, correct?
Right. Yeah. Each question will be worth, I don't know. Each question on the assignments, the number 7s are worth 3, and we break the question up into parts. So we give you marks for the work and the theory part, just the potential difference is E times L or whatever. If you know the definition of that, there's some value in that. So we try to find marks where we can. So it's not just right answer, wrong answer. We do try to look for your understanding and grade that. That's the benefit of written solutions and handwritten grading.
And the questions, will they be submitted on Canvas like the assignment questions?
They will be, you will submit them in Canvas like you do number 7 on our assignments, yeah. As a PDF file.
All right, thank you.
And you can do them on your tablet too if you want, so long as your tablet, you do not access the internet with your tablet while you're doing it. Like do not access resources contrary to your integrity statement.
All right, great, thanks.
Your own honor in that sense, but yeah. And I think Professor Kudel really likes engineering a graph paper, so if you can find a template for that, that helps too. Okay, anybody else? I really appreciate everybody's efforts they put into this class. I know it's a lot of work and it's fast. This and computer science last term are both delivered fast.
Yeah, they were very fast.
Yeah,
I don't know if you'd be able to tell us this, or if you even know, since you haven't made the questions yet, but do you think there would be a charge distribution question? Because that's the one thing that went by so fast for me that was very confusing.
What do you mean charge distribution?
Like where you have to use the lambda and sigma with the weird shapes and see where the charge is.
Oh yeah, yeah. If we do a question like that, the point of the question is not going to be to figure out if you understand how charge density works. It's going to be to figure out if you understand how electric fields and potentials work. So we try to provide a shape that makes sense, like that's pretty obvious that it's area times surface charge density, like for areas. Hopefully it shouldn't be too complex.
Okay.
Yeah, but I can't say that for everyone because I don't know how complex it is for some people. But
yeah,
like if we provided a sphere with if let's say assignment 1 example or question 7, it had a cylindrical tube, and you had a surface charge density on that tubular surface, which is just a rectangle like wrapped into a tube. That's possible, but we're trying not to trip you up at the start so that you get stuck and can't do the rest of it. So
right, okay.
Yeah. But we do hope that you can do basically simple multiplication of density times an area, or volume density times a volume, or whatever.
Yeah. Okay.
That makes sense. Yeah. So know your surface area of a sphere, surface area of a cylinder, volume of the cylinder, volume of the sphere. Know those things.
Okay.
I don't think they're on your formula sheet actually. Maybe they are. Well, it was nice to meet all of you, and you know, it feels to me like everybody's working really hard. So well done. I know it's a lot, but I feel like everybody's hanging on and trying to keep up. So well done. And I'll see you in the help desk tomorrow if anyone goes to that. Okay.
Thank
Thanks
you.
everybody. Okay. Take care. Good luck. Stay safe. Thank you. Thank you. Thank you. Appreciate it.